Welcome to lesson 1.2. We're talking about the slope of a tangent today. So we've talked about this before in the advanced functions class. There, though, we were always approximating the slope of the tangent. So just to review that, to approximate the slope of a tangent at point P, that's the point that we're given and that we're interested in, we choose a point Q that's close to the point P and calculate the slope between those 2 points. Now, the closer I can slide that point Q to the point P, the better the approximation is going to get. So first I'm going to show you a visual example and then we'll look at a calculation example. All right, so here I've got a curve. Here you can see my f at x curve in red, and I want to approximate the slope of the tangent at point P. So I'll add that to my illustration. This is the line that I want to find the slope of. So what we do is we pick a point Q that's kind of close to P, and we create this secant between those two lines, and we can calculate the slope of that secant using our slope formula from grade 9 or our average rate of change formula. We also call that the difference quotient. But as I slide that point Q closer to point P, what you notice is that the slope of this line becomes more accurate, and it's actually going to be a better and better approximation of the slope of the blue line, the tangent line that we actually are looking for. So, an example with an equation here, we've got a parabola, and we're going to approximate the slope of the tangent at the point where x is equal to 2. So I can do that by picking a point Q where the x value is kind of close to 2. I find the y value at that point, and then I calculate the slope using that slope formula, and I find that the slope is about 1.5. Then I slide a little bit closer. So that's the slope of the tangent line when I'm half a point away. Now I'm sliding so I'm only 0.1 away from the point I'm actually interested in, x equals 2. I find the y value, I find the slope, and now it's 1.1. So I'm getting a different answer here, and I'm probably getting closer to the actual slope of the tangent. I can slide a little bit closer, and this is usually where we ended up in advanced functions, 0.01 past the point that we are interested in. And there I come out with a slope of 1.01. So if I take a look at these slope values, what I notice is that they're getting closer to 1. And so I would say then that I believe if I kept going and getting closer and closer to the point P, it appears that the slope of the tangent at P on f at x is actually equal to 1. But I am approximating and I am guessing. So in general, what we're doing here is we're saying that as the point Q approaches, remember that arrow means approaches, so as Q approaches P, we can see here in the diagram, so I'm picking a point Q here, and then I slide it a little bit closer because what I care about is this point P down here. So I'm taking that point Q, sliding it closer, finding the slope of all of these secants, and it's going to get closer to the slope of the actual tangent line at P. So as Q slides towards P, what I also notice is the A rock approaches the I rock. Or another way to say that is the slope of the secant approaches the slope of the tangent. And the other thing that we notice in this formula here, this is our slope of our secant formula, or what we call the difference quotient. In that formula here, what's happening is the h value that I'm adding to the point that I actually care about is getting closer to 0. Right? So why don't I just make it 0? Like, why am I getting closer and closer to 0 but not actually doing that? Well, if I plug 0 into this formula, I'm going to get some value divided by 0, and I can't divide by 0. So that's why I can't just simply plug 0 in. So remember that this is called the difference quotient. So what we do in calculus, if I actually want to find the slope of a tangent, what I do is I take something called the limit. So this is our first lesson involving limits. We're going to do several, and as we do each lesson, it's going to help you get a better and better idea of how to deal with limits in math. So first, what I notice here is the slope of the tangent is equal to this limit, and we're going to talk about how to read that, of the difference quotient. So we read this as the limit of the difference quotient as h approaches 0. And we're going to talk about doing different types of limits, but specifically today we're using limits to find the slope of a tangent. We'll use limits to do other things in future lessons. So the slope of the tangent is the limit of the slope of the secant as the point Q approaches P. We're looking for the limiting value. Okay, so how do I find the slope of the tangent and evaluate those limits? So what we're going to do is follow these steps here each time. First, we're going to find f at a. So find the y value for the x that you care about. This is going to be a number because they're going to give you an x value. Then we're going to evaluate f at a plus h. Now, h is that value that's shrinking and getting closer and closer to 0. I don't actually have a value for it in this course. We're not using 0.01 anymore. So this is going to be an expression in h every time. There's going to be a variable. And then I'm going to evaluate the limit. As I do that at each step throughout my work, I'm asking myself the question, can I evaluate the limit yet? Which means, can I sub in the value for h yet? And if not, I'm going to keep simplifying the expression until I can sub in the value for h. So let's take a look at what those steps look like in an actual example. We're determining the slope of the tangent to the function at the given point. So we've got the function f at x equals x squared minus 3x, and we're going to look at the slope of the tangent at x equals 5. So like they said, my first step here is to find the y value at that given x value. Okay, so the y value is 10. Then I'm going to plug into my equation the expression 5 plus h. That's my a value that they gave me, 5, plus h. And remember, I'm leaving the h in there as a variable. When you do this, it's really important to do the substitution with the brackets. So it's the whole thing 5 plus h that's being squared. So that's actually 2 brackets being multiplied by each other that I need to multiply out or expand out. All right, so when I FOIL these 2 brackets, I get 5 times 5. Then I get 5 times h, and then I get h times 5. So that's 5h plus 5h. And then I get h times h. And now I'm going to multiply the negative 3 into this bracket here. And now I'm just collecting like terms, and I'm going to rearrange it so that the degrees are in decreasing order. All right, so I've got my 2 expressions. Now I'm going to use that definition that the slope of the tangent is equal to the limit of the difference quotient. And I'm substituting in my a value here. As h approaches 0. Now, what I'm going to do next is ask myself, can I plug in h as 0? Well, no, I can't, because then I'd be dividing by 0. So I'm going to start to try to simplify this expression. So the first thing I'm going to do is substitute in the f at 5 is 10, and the f at 5 plus h is this expression here. So I still haven't taken the limit, so I still have to write it. Don't forget to write it until you take it. So first, our expression for f at 5 plus h, and then we're subtracting. You might want to put this in brackets, depends on how many terms there are here. I'm just subtracting 10, so I don't technically need the brackets there. And then that's all over h. All right, so I asked myself the question again, can I sub in the value h is 0? And no, I can't, because I would still be dividing by 0, which is not allowed. So I have to try to simplify this expression until I get something where I can plug in h is 0. So I still haven't taken the limit yet, so I still write it here. So now looking at the numerator, if I can simplify that, I get h squared plus 7h, and the 10s went away. That's the happy magic we were looking for. All right, now what I notice, again, I still can't plug in h is 0, so I still haven't taken the limit, but what I notice is that the numerator has a common factor of h. I'm going to take that out. And now what I have is the magic of canceling these h's. So I'm going to cancel, I've got an h on the top and an h on the bottom. Because it's a multiplication, I can cancel those out. And now what I've got is the expression h plus 7. And at this point, I can take the limit. I can actually pretend that the h value is something incredibly close to 0 and plug it in there. And what I would get is 0 plus 7 when I take that limit. And so the slope of the tangent is 7. All right, we're going to try a different example. So last time we were just starting with a polynomial. It was a quadratic last time. This time we're starting with a rational expression. So again, following the same steps at the top of the page, the first thing we're going to do is figure out what is the value of the function at the given x value. And so we get 2 over 4 or 1/2. Next, we're going to figure out what's the value of the function if we plugged in 1 plus h. So I'm just replacing the x in the formula with a 1 plus h, and now I'm going to simplify that. And I should still have an expression in terms of h. It's not going to go away at this point. Once I've got those two expressions, I can set up the slope of the tangent as the limit as h approaches 0 of the difference quotient. All right, so now I can't take the limit at this point, so I'm going to sub in my expressions. And we've got that stacked fraction kind of thing happening. I still can't plug in 0, so I still haven't taken the limit. I'm writing that down, that I still need to do it. So when I've got the stacked fraction, sometimes we like to instead write just the numerator and then dividing by h, so you can write it like this. I'm not going to do that, divide by h. I'm going to, at the same time, change the dividing into multiplication by the reciprocal 1 over h. And then I'm going to try and combine these two fractions here. All right, and I am taking the limit of this whole expression. So whenever it becomes unclear where what you're taking the limit of stops and the next thing begins, it's best to just take some square brackets or some extra brackets around the whole expression you're taking the limit of. All right, so we're going to take a look at that first bracket. I still can't plug in h as 0 because over here I would still be dividing by 0, so it's still not allowed. All right, in the first one here, in order to combine these two fractions, I need a common denominator. The common denominator is going to be 2 times h plus 4, just taking the two denominators together. And so the first numerator would have to be multiplied by 2. So I would get 4, and the second numerator 1 would have to be multiplied by h plus 4. So I am subtracting the whole expression h plus 4. Don't forget that you would have to distribute that subtraction through. And I'm still multiplying by 1 plus h. All right, I still can't take the limit because I can't plug in h as 0 for this second one. When I take a look at this first numerator, though, I can do 4 subtract h subtract 4, and 4 subtract 4 will give me 0, and I'm just left with h. And this is the happy magic. Because now what we have is all multiplication in the numerator and all multiplication in the denominators, and I have a factor of h on the top and the bottom. So those guys cancel out, and I'm just left with this expression. And at that point, once that h cancels out of the denominator, you're pretty much on your way, because now I can substitute in the h equals 0. Oops. So now I'm actually taking the limit, so I'm not going to write that notation anymore. I can sub in my value, and so I get 1/8. Sorry, this should be negative. What happened here? Up here, I lost my negative. This was negative h. Negative, so this is -1, so this is -1, so this is -1/8. Hopefully you made that correction. All right, so therefore, Now remember, this isn't going to be the slope of the tangent everywhere on g at x, right? So you have to tell me that it's the slope of the tangent when the x value is equal to 1. The slope of the tangent will change depending on where I am on the curve. All right, next we're going to talk about evaluating limits involving radicals. So if I can't find a way to simplify to eliminate the h in the denominator, what I can do is try rationalizing the numerator. Now, usually we rationalize the denominator like we did in lesson 1.1, but we're going to try rationalizing the numerator so that I end up with something that will cancel with that pesky h in the denominator. So again, I'm following the same steps as before. First, I'm going to calculate the value of the function at the given x value. Now, they actually already gave it to me. It's 3. Don't do extra work. You don't have to. And then I'm going to figure out, well, what is f at 0 plus h? So that's the same as f at h. So I'm really just replacing the x in the equation with an h. All right, so now I can find the slope of the tangent. So remember, to find the slope of the tangent, we take the limit as h approaches 0 of the difference quotient. And then I'm just replacing that with the expressions that I've created. You don't have to do this work off to the side, but it just seems to be less confusing if you do it that way and then substitute it into the expression. All right, so there's that pesky h, right? And he's still in the denominator because he's part of the difference quotient. I can't get rid of him, and there's nothing really I can do to simplify the numerator, so I'm kind of stuck here. So we're going to use the trick of rationalizing the numerator. So remember, when we do that, what we're going to do is multiply the expression by that form of 1. And this time I want to create a difference of squares in the numerator. So I'm finding the conjugate of the numerator. So it's just the whole first term. Kind of gross, right? And instead of subtracting 3, I'm going to add 3. And then I'll do the same thing in the denominator. It's getting a little bit bigger, but hopefully some magic will happen and we'll be able to cancel that pesky h down here. That's our goal, right? To get rid of him and then be able to plug in all the h's. All right, so I'm going to take the limit of this whole thing. All right, now when you do this, remember that you're hoping that the h cancels. So don't expand the h into this other expression. You want it factored out because the goal here is for it to go away. So in the numerator, I am going to expand this. Remember, it's that difference of squares pattern we created by using the conjugate. So I really only have to multiply the first term times the first term. So 3/4 times 3/4, that's 9/16. And then the root times the root, well, that'll be the root squared, and so the root and the squaring cancel out. And then the middle two terms are going to cancel out. You're going to get -3 times that big mass, and then +3 times the big mass. It'll cancel. -3 times +3 is the only term left, and so we end with -9. And then remember, in the denominator, we're not expanding. You want it factored. We love factored. All right. So let's try to simplify this numerator. We're hoping that an h will pop out that we can then cancel with the denominator. So I'm going to take the 9/16 and multiply it into this bracket. I can't take the limit yet, right? Because if I did that in the denominator, I'd get 0 times some stuff, and that would just give me 0. So I've got 9/16, I'm going to multiply it by 16. That's just 9. And then 9/16 times -h squared. Oops. And then we've got the -9 here. And there's our good news, right? That's a subtraction. Okay, so now I've got 9 minus 9 in the numerator. So those guys are going to cancel out to 0. And then I also have in the numerator, now I've got all multiplication, -9/16 times h squared. So that means I've got a multiple of h on the top and a multiple of h on the bottom that can cancel. So the h, and now instead of h squared, it's just going to be h to the power of 1 that's left over. So now I've got -9/16 times h all over that messy bracket. And now that that h is gone from the denominator, you can plug 0 into this expression and you're not going to be divided by 0. So we're going to actually take the limit here and we're going to plug 0 in for all of those h's. So that's when my limit notation disappears, right? When I can do the substitution. All right, so the numerator comes out to 0, the denominator comes out to some value, right? Like I can take the square root of 16 is 4, and then I get 3 here, 3 plus 3 is 6. So I get 0 over 6, but that's just 0. So therefore, okay, the last thing that we're going to be asked to do in this particular section is finding the actual equation of the tangent. So it's nice that you know the slope, but what's the actual equation of that line? So we already know how to find the slope, just like we did in example 1 and in example 2. But now we actually go a little bit further and find the value of b, which you might remember we did in lesson 1.0, that prerequisite skills. You just sub in the slope and one of the points that you know, and then you can figure out the equation y equals mx plus b. All right, so we're starting again by finding the slope of the tangent. The first thing I'm going to do, because I don't like it when it's called y, I would rather use function notation. So the first thing I'm going to do is name this guy. I prefer f at x, but since we haven't used function notation yet, you can use whichever you like. Maybe you like g at x or k at x. Then I'm going to figure out the y value for the given x value. Now it was already given to me, so I'm not doing any extra work. I'm going to trust that they're right. And then I'm going to plug in 2 plus h. When I do that, again, I'm putting brackets around it. If you've got data management, you might have a trick for this. I'm going to do 2 plus h times itself, and then I'll have to multiply by 2 plus h one more time. So first I'm just going to figure out what is that binomial squared, and then I'll multiply by 2 plus h again, and then I'm going to add the 2 plus h, the last bracket there. So many 2 plus h's here. So first, squaring the binomial, we get 4 plus 4h plus h squared. If you're not sure where I got that middle term, you can take an extra step and multiply it out and then collect like terms. Now I'm going to multiply the 2 into this whole bracket. So I'm kind of reverse distributive here. And then I'm multiplying the h into the whole bracket. And then I'm adding 2 plus h. Now I'm going to collect all my like terms. All right, and I've got my expression. So next I'm going to find the slope of the tangent. And again, in calculus, we are always now finding the slope of the tangent by using the limit. We're using calculus techniques, not advanced functions techniques. All right, so again, I can't plug in h is equal to 0 yet. I can't take the limit yet. So I'm going to substitute in all my expressions. And then I'm going to try and simplify. And so like we've seen before, what happens here is the 10s cancel out at the end, and I see that there's a common factor of h. So I'm going to bring that out. Again, I haven't taken the limit yet because I haven't canceled away. So I've got my h. And now the h's are going to cancel away. And I'm left with an expression that I can take the limit of. Now, at this point, it is necessary for you to put brackets around. So this is not an optional thing. You do have to have brackets around this expression. Otherwise, it looks like you're taking the limit as h approaches 0 of h squared. And once you find that answer, then you're adding 6h plus 13. So we want to actually take the limit of the whole expression, not just the first term. So now I'm going to plug in my 0 for my h. I'm actually taking the limit, so the limit notation disappears, and I get 13. So now I know that the slope of the tangent is 13. I can actually find the equation of the tangent now. So I know that the equation of a line is y equals mx plus b, but for my line, the slope is 13. To find the b value, the y-intercept, we're going to plug in a point that we know is on the tangent line. Well, the only point that I know that's on the tangent line is that point that they gave me originally, 2, 10, right? We've got some sort of like curve here, right? And they've given me the point 2, 10, and that we're doing the tangent line through there. So we do know that point here. We're just trying to figure out, well, where's the y-intercept? So we're plugging in 10 for the y, and 2 for the x. Now we just rearrange and solve for b, and we've got it. Don't forget to write the actual equation. This is the final answer here. So that needs to be somewhere. All right, and that's it for today's lesson. You can find the homework on the homework log. Have fun.